Now we're going to introduce the most important invariant of a partially ordered set. It's called the Möbius function. So we start with the general setup. Given a poset P and a function in incidence algebra, so a function on the intervals of P to the complex numbers, when is that function invertible? Well, what does that mean? That means that when you convolve f with the inverse of f, and apply that to the interval PQ, then you should get 1 when P is equal to Q and 0 otherwise. Because remember, the unit multiplicative identity, the incidence algebra, is this one. And recall, of course, whenever I say the ordered pair PQ, I'm talking about two elements in the poset such that P is less than or equal to Q. So as we've done with other times we've talked about inverses, we start to check conditions. We want 1 when P is equal to Q, so that means that F convolved with G applied to PP should be 1. But in terms of the convolution formula, what should that mean? Well, you sum over all elements in the interval PP, but there's only one element, that's P itself. And so the summation formula becomes just this one term. And so if we want this to be 1, we see that f of PP has to be non-zero. Otherwise that would make that 0 for every element in our partially ordered set. And then we see what g of PP has to be. It has to be the reciprocal of this. So when you multiply it out, you get 1. Now, that tells you what the inverse, a formula for the inverse over ordered pairs intervals P and Q where Q is equal to P. What about the general case? For P strictly less than Q, we require this convolution when applied to the interval PQ to be 0 by definition. But by definition of convolution, that should be this formula. We're summing over all R in the interval PQ, f of PR times g of RQ. And so we want this to be 0. And so we could try to do some sort of recursive argument. Supposing that you know a bunch of these previously computed values, you only need to compute one more. And that's exactly the formula we see. Define g of PQ to be -1 over f of PP times the summation over all R in the interval PQ, such that R is not P. F of PR times g of RQ. And so if you use induction on the number of elements in the interval PQ, this formula is well defined because these entries on the right hand side correspond to intervals with fewer elements. So we know that these values have previously been defined, and so this is defined. And by the way this formula is set up, it's set up in just the right way that when we do the convolution, we get the unit. And so in conclusion, the multiplicative inverse is an element of the incidence algebra if and only if f of PP is non-zero for all elements in the poset. And we see that turns out to be the only restriction we need. And once that happens, this formula gives you a formula for the inverse. And the standard example in this theory of partially ordered sets is the Möbius function. If you can't write it with the umlaut, it's often written this way as well. Yes, the same mathematician the Möbius strip is named after. And that's the multiplicative inverse of the zeta function. We'll call the zeta function as 1 for every pair of elements when P is less than or equal to Q. So by this formula, zeta inverse of PQ is negative of the summation over all R in the interval PQ. R is not P, zeta inverse of RQ. So I'm just plugging in this formula and writing zeta inverse here. Since zeta of PR is always 1, that term disappears. Since this is always 1, that term also disappears. So the formula is a little easier. And for historical reasons, instead of writing zeta inverse, we'll write mu for Möbius function. And so this is the definition of the Möbius function, or a recursive definition. is defined in terms of previous Möbius function values. Note, everything I did multiplication on the right. If you do multiplication on the left to define the inverse, you'll get this formula for the Möbius function instead. Notice the difference. Here we're varying the first coordinate. Here we're varying the second coordinate. So here, these first coordinate are all entries that are strictly bigger than P. Here the second coordinate entries are strictly less than Q. So just for clarity, this is the Möbius function for a poset. And so it goes from the incidence algebra of a poset to the complex numbers. It's defined recursively by this formula, with the other remaining case that mu pp is always 1 as the base case. And then for all non-trivial intervals that have more than one element, it's defined recursively by either of these two recurrence relations. So now let's look at our first major example. Let's compute the Möbius function for the natural numbers. So the natural numbers are just pairs. We're looking at pairs of integers ij, where I is less than or equal to j. By the recurrence relation, mu of ij is the summation over all k less than j, negative of mu ik. So I'm varying the second coordinate. With the base case that mu ii is 1. So we can check based on this recurrence relation that mu ii plus 1 is negative 1. Why? Because there's only one integer. Oh, I forgot to put the other restriction here. I is less than or equal to k. As you range from I less than or equal to k strictly less than I plus 1, you've only got one term. Its value is 1, but you're negating it, so it becomes negative 1. Now let's compute mu of I plus 2 by the summation. These are the two terms with the negative signs. Mu of I plus 1 is negative 1. Mu of I is 1. And so here we see we get 1 minus 1, which is 0. Similarly, if we look at mu I and I plus 3, there's only 3 terms in this summation. This first one is 1. The second one is negative 1, and this last one is 0. And then when you negate them, you get negative 1 plus 1. So we see you get 0. And now you start to see the general pattern. If you look at mu I plus k, these two terms cancel because they're 1 and negative 1. And then all the other terms you've computed previously to be 0. And so in general, mu ij is either 1, negative 1, or 0. It's 1 when I is equal to j. It's negative 1 when I is right before j, like this. And otherwise it's always 0, because we get this cancellation property. And so we'll see this pop up again in a later lecture, but this is the Möbius function. This is also the Möbius function for n, which is the set of integers with the natural ordering we're used to. The same Möbius function will happen for the exact same reasons. And so this Möbius function works for chains as well, and we'll sometimes take advantage of that. As another important example, let's compute the Möbius function for the power set of a finite set x. So here we are assuming x is finite. So you're looking at intervals. What does intervals in this poset look like? There are two pairs of sets, S and T, where S is contained in T, and T is a subset of X. By definition, because you're working with intervals in this partial order, and it's worth pointing out we're ordering by inclusion. And so recursively, the Möbius function is this negative of the summation over all R. S is a subset of R, which is a proper subset of T, mu of SR. So let's look at an example. Suppose you're only one element bigger. T is only one element bigger, then when this sum only has one term, it's mu SS, which is 1. You're negating it, so you get negative 1. Now let's suppose T is bigger than S by 2 elements. Let's call them X and Y. When you do this summation, you see you've got 3 terms, S union X, S union Y, and S. Negating them all. These two look similar to this, so they have formula negative ones. So when you negate them, it's plus 1, plus 1. This one is 1, so it's negative 1. So you see you get plus 1 as the result. Now suppose T was bigger by 3 elements. Well, then you've got 3 of this form, where you've taken your favorite 2 elements of this set and kept them. 3 where you've only taken 1 of those elements and kept it, and then 1 version where it's by itself. We just computed that this value should be 1, so that's a negative 3. This value was negative 1, so this becomes a positive 3. This value was 1, so this becomes a negative 1. So you add up and you get negative 1. And so I'm seeing 1, negative 1, 1, negative 1. It looks like it's alternating and always 1 in absolute value. So we see, based on our evidence, that we expect the Möbius function to be alternating in sign with absolute value 1. And so one way to prove this is to use induction and show that this function satisfies the same recurrence relation as the Möbius function. In other words, that this summation is either 0 when S is a proper subset of T, and 1 when S is equal to T. Because that would make this function, negative 1 to the size of T, take away S, equal to the inverse of the zeta function. Why? Because that's the definition of the inverse of the zeta function. If I put mu st here instead, I get exactly this recurrence relation. And so showing I satisfy the same recurrence relation and the same initial conditions. And so let's do this proof. Well, this is not too bad. The first thing we can do is, so I want to show the summation R, such overall subsets R, such that R contains S and is contained in T, negative 1 to the, that shouldn't be T take away S there. Let me redo that part. That should be R take away S. Now the first thing we're going to do is I'm going to define S prime to be R take away S. And so we see as R ranges over all subsets of T containing S, S prime is a subset containing the empty set contained in T take away S. And vice versa, given such an S prime, I can take the union with S and I get a subset R over here. And so there's a bijection between these two collections of subsets I'm summing over. Moreover, negative 1 to the size of R take away S is negative 1 to the size of S prime under this bijection. So these two summations are the same. And now I'm going to do the usual trick. I'm going to collect subsets based on their size. Their sizes range from 0 up to size of T take away S. And sum over all subsets of that size. I should actually include that in here. S prime has to be of size K. Now this exponent becomes a K. And then we see it no longer depends on K. So, no longer depends on S, so I can actually move it outside the sum. And then sum over one thing at a time. But then I see that means that this summation of 1 is just this collection of sets. And these are subsets of size K, so this is just a binomial coefficient. I apply the binomial theorem, realize that this is just a binomial convolution of 1 and negative 1. And so I get 1 minus 1 to the power of size of T take away S. But 1 minus 1 is 0. And in combinatorics world, 0 to 0 is 1, and 0 to any other power is 0. And so this function satisfies this condition. And so we see that this is the Möbius function for the Boolean poset. I should recall, if I haven't actually written it down yet, Boolean poset is the fancy way of saying this collection of power sets of a finite set X under inclusion. And so there we have two important examples of Möbius functions. So in general, given a partially ordered set, a normal problem a common torus asks is there a nice formula for the Möbius function? And when we see Möbius inversion formula, you'll understand why. Or it's worth pointing out this formula looks a lot like the powers you see in the principle of inclusion-exclusion, and we will eventually see that there's a natural reason why you expect that.